Hello, students. Today, I'm just going to sort of jump on this PhET wave interference simulator and have some fun. Just kind of show you some different things that it can do. The point for an inquiry lab is to just kind of explore, see everything that this simulation has to offer. There's all sorts of different labs that we could, do with this simulation. If you think about the learning objectives, there are learning objectives related to diffraction and interference and, two slit and multiple slit interference. And there's even like part of the simulator here with just sort of one source for waves, and so no interference, but a chance to maybe review some of the learning objectives that we've already studied. So let's just jump right in here with a single pulse of sort of a water droplet sent into this medium of water molecules, and we'll jump right on in with a cannonball. Boom. There's the disturbance. There's the transfer of energy. You saw the waveform. And we could also have a steady sort of dripping of the faucet here and have a periodic disturbance. Hey, there's a vibrating medium. That medium is oscillating up and down. The water level is going up and down at different points there. All right. So in computer science, there's an acronym RATS, read all the screen, and you should really just kind of, always take a look. What's everything that we can kind of do here? Don't worry about that. Might be needing that later. Drawing tool. But we could, look at waves, interference, slits, and diffraction. Just in waves, we've got sort of different sources of waves, some water waves, sound waves, light waves. Right, so we can get all those kind of going there. So you can see with sound waves, it's a change in pressure. There's different sort of things you can do in each one of these. So we can look at, a graph of pressure against position. We can see particles instead of the waves. You can see both. All right. For light, you can just sort of see a screen here. And as this light arrives, we see a bunch of light on the screen. Okay, that'll be more handy, I think, when we're trying to observe interference. We change the amplitude, so the brightness of the wave, or how much the electric field is oscillating over here. We could make it lower amplitude. We could change the frequency of the light, so sort of a dark red light, yellow laser, a light blue laser. Kind of cool. Almost looks like a water wave, right? Violet, purple. I don't know if we can get the ultra purple. I don't know. Anyway, you get the idea. Read all the screen. Side view, top view. I don't see how that really changes there, but I suppose with a water wave. All right, so think about the learning objective, describe the motion of transverse and longitudinal waves. We know that sound is a longitudinal wave. If you take a look at any one of these particles here, you can see that they're moving parallel to the direction of transfer of energy. So the wave is moving from the speaker across the screen from left to right. And take a look at this red particle right there. Let's kind of clean this up a little bit. Pull back away there. You can see that it's moving left and right, but it's oscillating on the spot, right? So the wave continues on. The particles just sort of crash into their neighbors and they oscillate backwards and forwards at the frequency that they're being sort of pushed at from the source over here. Cool. The learning objective to describe waves in terms of their wavelength, amplitude, frequency, speed, and intensity. All of those things you could kind of, explore just in this screen right here, waves. Take a look at the water waves here. So here we clearly see like the transverse sort of nature of it, how it's moving up and down as the particles move left to right. But we could also like measure the wavelength, with that tool. We could time the number of waves passing by a point. We could mark out a point, like say where this point is, and count how many waves pass by in a certain amount of time. right? Waves per time, that will give us the frequency of the wave. Here we can kind of qualitatively manipulate the frequency, how often the drops are falling into the bucket of water here, the virtual cube of water. You make the drops bigger to get higher amplitude, or make the drops smaller to get lower amplitude. So I think we can even measure the amplitude sort of on this scale. So each one of these squares is 1 centimeter. I think we can get 1 centimeter of amplitude, at least initially. Well, let's see what happens. At maximum, it looks like the amplitude's like 1.5, and the first wave kind of like right here, like the first one that's sent off, it's just under 1 centimeter. So we kind of see how there's less and less amplitude in the wave because it's sort of spread its energy out the further it gets away from the source. Think about how these waves are spreading out in a circle in all directions, and so the energy at the source is dissipating sort of in all directions, and so the amplitude of the wave is going to decrease because the intensity, which is the power per unit area, and power, remember, is the sort of rate of arrival of energy from the wave. So the intensity is proportional to amplitude squared. That's something that you may recall from your reading. So we talked about wavelength, amplitude, frequency, speed. Once we know the frequency by counting the waves and dividing it by the amount of time that it takes that many waves to pass by, then we can multiply that frequency by the wavelength and get the velocity of this water wave. It'd be really cool to do that for light. You can see that they've our tools here are already calibrated to sort of friendly units, and so our ruler here is set to 500 nanometers, and our clock is measuring in femtoseconds, and there's even like a friendly conversion up here that tells us a femtosecond is 10 to the negative 15 seconds. And so here's sort of all the tools we need to deduce the speed of light. Pretty cool. We'll save that lab for another week. We talked about intensity, how it relates to amplitude, frequency, speed. So that was already, one of the previous learning outcomes. We're already like 7 minutes in, and we haven't even got to the interference stuff. So let's take a look at that. Oh, speaking of which, you could also take a look at the principal wavelengths of the EM spectrum. So while here we're only looking at the visible part of the spectrum, we could at least remind ourselves that visible light kind of goes from around 400 nanometers. Here they have it down to 380, all the way as long as they have it closer to 800 nanometers. You may recall from the reading that I think I said between 400 and 700 nanometers is sort of where visible light is. And so here, if we say this is, let's call that red, right there, 700 nanometers, that's clearly red. See how that's infrared? Yeah, I mean, our eyes can't usually detect it, but I would call this infrared. We'll say, well, 800 nanometers is still red. We could see 800 nanometers. All right, but the way I prefer you learn it is between 400 and 700 nanometers is where we can sort of observe light. And yeah, maybe we can detect light a little bit longer. What's a couple of hundred nanometers between friends? All right, let's go into the learning objectives associated with superposition of waves. Explain and use the principle of superposition of waves. Okay, well, when two or more waves meet at a point, the resultant displacement is the sum of the displacements of the individual waves. So that's sort of just like a good way to think about the principle of superposition. We could set up a little experiment here to kind of show that. And so let's have a water wave here. Okay, and let's make the amplitude like half of this, of what we can sort of maximize it to be. I'll put this sensor here, right here, so that I can sort of observe a crest right at this point here. All right, and you can see that the amplitude is right at the point here on this screen. The water level goes up to here. All right, the principle of superposition says that, like, let's say I turn on this faucet now. Well, when the crest that would come from this wavefront meets the crest from this wavefront, then we should be able to add this up and it would be sort of like twice them. And so we should see this sensor sort of kind of double in size at the point where both of the crests would be meeting. And so that might be like here, right? So by the time we'll actually be in between both of them, right? So let's see if we don't observe that. So now I think we kind of got this one right here. And so now you see the displacement is higher, right? Because by the time this crest sort of makes it there, it's combined with this crest, and so we get sort of like a double crest. Maybe we should show it sort of out here. All right, so let's see how the height is tall when there was still interference, and then it's decreased once sort of all of the energy from this wave had already sort of gone through the medium. Now we only have drops from this one, and so you see how the height is just down there. All right, let's turn this dropper back on. The principle of superposition, again, states when two or more waves meet at a point, the resultant displacement is the sum of the displacements of the individual waves. So you've seen how the displacement is increased. We're adding those waves up here. Pretty cool. So that's superposition, adding waves. The learning objective, explain experiments to show diffraction and interference, we can cover in this simulation also. Diffraction is the spreading of a wave as it passes through a gap or around an edge. And you may be tempted to just click sort of over here on diffraction. Well, let's just do that. So we can see, yeah, the spreading of a wave as it passes through a gap, right? Cool. As I mentioned, we could kind of, manipulate the frequency here. My favorite color is 510 nanometers. That's the best shade of green. And here we have a gap that's circular, and we get this kind of a pattern. With the square gap, we get this kind of a pattern. If we've got a square gap and a circular gap, then as the light goes through each one of these gaps, it's going to diffract, and then those waves are going to overlap here, and they're going to superpose, right? So we can apply the principle of superposition and add the waves that we observe on the screen. So that all relates. You can have a bunch of gaps, and sort of all of the waves that are diffracting from each one of these slits that emerge are going to meet in space, and we're going to add up all of those different waves and get sort of an interesting pattern like this. Pretty cool. And we could even use lasers to kind of image things, right? We can kind of see how that kind of looks like that. And so as the laser light is diffracted through this, we get an image over here. And the scale of this is only 0.1 millimeters, but over here we're looking at something that's like 10 millimeters, right? Centimeter. Cool. All right, let's take a look at some interference here. Let's do with sound waves. All right. Speakers were connected to the same signal generator playing the same frequency, then the waves generated will be coherent. They have a constant phase difference. That is to say, they have the same wavelength, and therefore the same frequency, and it remains the same over time. When two coherent waves meet, they will superpose. So we apply superposition and add the waves. What we observe on the screen, a pattern of maxima and minima, are places where the waves have reinforced and constructively interfered, and canceled where the waves destructively interfered. Crest meeting crest adds up to big crest, loud spot, right here. Crest meeting trough cancels out, adds up to 0, quiet spot. Notice how when the waves have to travel an extra half a wavelength compared to the other wave, that is when we'll see destructive interference. When waves travel one whole wavelength or some other integer multiple of wavelengths longer compared to their coherent twin wave, then constructive interference results. The alternating pattern of maximum, minimum, maximum, minimum, that's what characterizes a wave. Now, this pattern was so well known for waves that when it was observed for light for the first time with candlelight, it was an experiment done back in the early 1800s, well, it led scientists on a path to think of light as a wave, which we certainly can. There's a little bit more to it than that, and I'll save that discussion for another time. Physicists are still kind of in the dark about light. Note that we can see the interference pattern in different types of waves, and note with this sensor what we're actually measuring with the different types of waves. Right? The electric field sort of that's oscillating. So here, along sort of these lines right here, we can sort of see it with our eyes that the waves have canceled out. That's where crest is meeting trough, and the superposition principle is applied. The wave adds up to 0. We can even measure it with this sensor right here, and you can see that the dark gray sensor is hardly moving at all. Whereas in a place of maximum, we can see the electric field oscillating the most. And so again, this alternating pattern of maximum, minimum, maximum, minimum, maximum, that's the interference pattern, the points of cancellation and reinforcement that we know waves can do. So waves interfere. So this led scientists to think that sort of, well, light must be a wave. And it certainly has wave properties. Remember, we're measuring water level. With water waves, we're measuring a difference in pressure from the constant sort of air pressure with sound waves, and we're measuring that oscillating electric field for light waves. So in summary, for interference, we just want to be able to state how interference is the formation of points of cancellation and reinforcement where coherent waves meet. Now, the final learning objective relates to solving problems involving two-slit and multiple slit interference. So multiple slit interference is a diffraction grating. The physics is much the same for two-slit interference. And in fact, the equations that we typically use to solve problems are really the same. They're just kind of put in different forms. And we see we've got the ability to explore with slits here. Well, we could kind of see, let's clean that up. We could kind of see diffraction just by sending like a wave through a gap, right? We know that the wave is going to do what when it goes through a gap? Well, it's going to spread out. And so, yeah, we can observe diffraction with like a single slit, and you could see that as we make that slit more narrow, the wave spreads out more. As the slit becomes larger, the wave doesn't spread out as much, right? And so that's kind of a conclusion that we could reach there. Now, with the sort of laser interference pattern, typically we wouldn't be able to achieve this in a lab if we used two separate lasers, even if they were sort of tuned to the exact same frequency and it was the same color light, because of the sort of nature of lasers. Laser light could have a constant or a sudden shift in phase, we can kind of think about the laser light as coming out in sort of pulses or packets. So the way that we achieve sort of an interference pattern with laser light is to send a single laser through two slits. Here we can kind of see our laser light generator, and here we kind of see the wave nature of it. And the waves are going to diffract, and what do we observe over here? Again, our characteristic pattern of maximum, minimum, maximum, minimum, maximum, which is due to the coherent waves meeting, reinforcing for constructive interference, canceling out crest meeting trough for destructive interference, points of cancellation. We'll be able to use this simulation to do sort of more experiments. I can see them already sort of like past 20 minutes here. I tried to review a lot of the learning objectives. Your goal, remember, students, is to do your best to master those learning objectives. Don't stress about it too much. If you're watching this video that, and you weren't able to, for whatever reason, you didn't have the software, or your computer wasn't working, but sometimes you need like an Adobe Flash add-on player, those kinds of things, and your computer crashes, when you try to do it, or, so I understand. The fact that you're watching this video, hopefully you got something out of it. Just keep a record of what you're doing in your journal there, and have fun.